So this is a collection of many of the robots we saw or wished we were going to see. So I'm going to kind of use them as different examples of what's going on. But what we're going to do is we're going to go in and we're going to jump into the very first robot that we talk about. And I think this is the Kawasaki MG15HL, something like that. So HL probably stands for heavy lift. And just to give you an idea of the size, that's a person standing next to it. And obviously I could not get that close. It was fenced off. And, I tried my best to almost break the safeguards on there until someone came up to it and said my fingers were getting too close. More on that later. But anyway, this is, definitely an articulated style robot, but the way the actuation is done is a little bit different. And what we're going to see is there are these actuators down there. And I just got to go ahead and get myself in the correct mode right now. So we can go ahead and we can move this robot. So you could see this is typically what we'd call the second axis. And actually the first thing I got excited about, if you remember, was I was pointing out the fact that it's got two motors. So it is so big, it actually needs two really big actuators just to make this first axis move. And the second axis we'll see also has two actuators. Whoops, zoomed in a bit too much there. Has two of them on there that are used to actually move the structure. And you'll see as it goes around, this ball screw changes in length. And again, as I pointed out, is that this is a parallelogram. And the thing about parallelograms is they are not stable unless you lock one joint. So a triangle is very stable. And if you add one more arm to a triangle, make it a quadrilateral, they will not hold themselves up unless you lock off one of the joints. So what's happening is that these joints here are all free moving, but this one down here is under control of that ball screw. It's what locks it into a particular position, and you change that and everything else has to move with it. Now you see they also put some counterbalances on here because sometimes when it's leaning forward, things are getting a bit tough here, and you've got a heavy payload on there, and that's just to counter it all. And then you have, so this very rigid kind of structure that moves around. Now the third axis would typically right where my mouse is, and you'll notice this one is offset over here. And again, more on that later. But what they're doing is they put a second ball screw drive up here, and you can see this ball screw actually also has two actuators on it. We're kind of looking at it from this side, and whoops, I moved to the wrong one right here. Let's get back. So we were looking at it from this side, and we can obviously see the first actuator here that makes joint one move around. And we can see over here is joint two, which goes ahead and makes this axis move forward. And again, they have this parallelogram, but it's a little bit different. You see, they don't have that connecting rod that goes in there. This thing is stiffly on out there the whole time. It seems like it's being used kind of as a counterbalance. And this rotation right there is normally where everyone puts their axis 3, because then you just push this thing up and down and axis 3 moves, and you can get the axis 3 motor down low. But it's not there. And axis 3 is actually happening up there. So remember when I came around there, at first I thought that motor was for axis 4, because it's a little bit thrown off why you would do that. But you'll see, and it's not Nachi that does it, it's Kawasaki, because that big beast we saw was the Kawasaki robot, remember? That's the picture I took. I mean, I looked at it for a second and I go, holy cow, it looks like a professional photographer. I guess I had my lens clean or something like that when I took it. But that's a really nice close-up that we could not see in the video of what those linkages look like. Like I said, there are no tendons in there. You can get an idea of exactly how that works, how they pull on that. Yeah, it's probably one of the best pictures I think I've ever taken, because this 4-bar mechanism is what causes that thing to rotate. There is no actuator there. It's unactuated. There is an actuator sitting right here that goes straight down that allows that to rotate. So it's really kind of a planar problem. So we can move back and forth this way with this motor. Then we have this motor here, which is actuating this thing. And the whole point of this structure here is to keep this upper structure in position that goes through this connecting linkage that we see right here. So that's the trick. And then we do have, again, some compressed air cylinders here that are used as like counterbalances, because we're lifting a heavy payload. We can see that big stretch. We don't want axis 2 to have to work too hard to be able to come itself back up. And don't be fooled by the fact that this is curved. You can consider that a straight line from here to there, to there, to there. So when you draw it out, you can consider them straight lines when you do the math, but there's no reason why they can't also be curved. And so this is a very, very popular design in palletizing because it's very rigid. It's very strong. It's fewer degrees of freedom. Yeah, you could use some 6-axis robots for this, but it's really hard to get that extended reach that you want. And heck, you don't need the fourth axis and you don't need the traditional sixth axis. So, how are you doing today, Marwa?
Yeah, good, but a lot of stress, as you can imagine. A lot of stress.
Yeah. Yeah. Well, we've got a few topics to cover today, which I guess we're going to break probably into 2 episodes. So, the first thing is, you remember that, I'm in a different studio right now than I normally am because I'm up here in Michigan. And the reason I was here is to visit the Automate show, which we had a nice little tour of last week, if you remember. So I was thinking is that maybe it would be good to do a little bit of a recap on that, exactly what we saw and what we did. And yeah, so we had a road trip or a field trip, if you want to think of it that way. And now that we've gone on the field trip, we were back in the classroom, and let's kind of discuss what we saw at the show. Are you ready?
I'm so much ready. Yeah.
Okay, good. So the robot road trip, and if you remember, we sort of began here outside the entrance to the halls in Automate 2025, which is the largest showcase in North America of robots and automation equipment. And I think it's yearly and it goes around different cities. I think next year it might be in Chicago and then it goes to Las Vegas. But also in a couple weeks' time, towards the end of June, is an equivalent kind of exhibition called Automatica, and this one's in Munich, and it's like much bigger. So we're going to see a lot of the same things, and then anyone's thinking of going there, hey, take a look at this because then it will educate your eye, and then you'll have an idea of what's going on. So if you remember, I began enthusiastically coming up to this bot because it was like the most fun bot that I'd seen at the show. It was the biggest one that was there as far as payload capacity and work envelope. And it also had a really complex kinematic. And the reason why this kinematics was really interesting is, remember, we did an episode called rotary versus linear debate and what kind of actuators you use. And I sort of stated unequivocally almost that, in modern day kind of articulated type of arms, you don't see the ball screw drives in them anymore. Everything is rotary. And this is the counterexample to that. So it's really rare, and why I was excited to see it. And it may not be obvious, but there's actually two. There's one up high, which is really unusual, and there's one down low that they really figured out how to package it in a more compact way. So if we go back to the 1980s, this is typically how a lot of robots are actuated, using these linear drives known as ball screw drives. And so it was a kind of a complicated mechanism because you had a linear actuator down here and a little pin there, and the nut that would go up and down that would help articulate this parallelogram structure in the back to, depending on which side you were on, to either make the third axis move or the second axis move. So there was no actual actuator in the middle. And, Cincinnati Millicron did it a slightly different other way, and ABB also did a classic way. Now, the one thing that's kind of disheartening right now is I've been trying to find images like this on the internet, and there are not that many of the older robots. It's really hard to find them. And it's kind of a shame because there's a lot of interesting kinematic designs.
No one using.
I Well, I think it's because the internet didn't exist in the late 80s, as far as uploading. It wasn't really to the 2000s. So you start to see a lot more of that. And I modeled all these things. We used to have them in our software, but you only see them in museums now. So they're not even in our catalog because they don't need to be there anymore. And that was also a little bit disappointing. It's like, oh no, why don't we keep those around? So anyway, um, and this is like a better photograph that I got rather than taking a video clip. So that video clip I had there was actually from the video. So everyone should go ahead and watch that at some point, and then you'll understand what I'm talking about here and why I'm going into it. So the first thing I want to do is now go ahead and actually share my other window here, which is going to be what I call the robot garden. Okay. So this is a collection of many of the robots we saw or wished we were going to see. So I'm going to kind of use them as different examples of what's going on. But what we're going to do is we're going to go in and we're going to jump into the very first robot that we talk about. And I think this is the Kawasaki MG15HL, something like that. So HL probably stands for heavy lift. And just to give you an idea of the size, that's a person standing next to it. And obviously I could not get that close. It was fenced off. And, I tried my best to almost break the safeguards on there until someone came up to it and said my fingers were getting too close. More on that later. But anyway, this is definitely an articulated style robot, but the way the actuation is done is a little bit different. And what we're going to see is there are these actuators down there. And I just got to go ahead and get myself in the correct mode right now. So we can go ahead and we can move this robot. So you could see this is typically what we'd call the second axis. And actually, the first thing I got excited about, if you remember, was I was pointing out the fact that it's got two motors. So it is so big, it actually needs two really big actuators just to make this first axis move. And the second axis we'll see also has two actuators. Whoops, zoomed in a bit too much there. Has two of them on there that are used to actually move the structure. And you'll see as it goes around, this ball screw changes in length. And again, as I pointed out, is that this is a parallelogram. And the thing about parallelograms is they are not stable unless you lock one joint. So a triangle is very stable. And if you add one more arm to a triangle, make it a quadrilateral, they will not hold themselves up unless you lock off one of the joints. So what's happening is that these joints here are all free moving, but this one down here is under control of that ball screw. It's what locks it into a particular position, and you change that and everything else has to move with it. Now you see they also put some counterbalances on here because sometimes when it's leaning forward, things are getting a bit tough here, and you've got a heavy payload on there, and that's just to counter it all. And then you have, so this very rigid kind of structure that moves around. Now the third axis would typically be right where my mouse is, and you'll notice this one is offset over here. And again, more on that later. But what they're doing is they put a second ball screw drive up here, and you can see this ball screw actually also has two actuators on it. And that's used to make this one articulate about this point. So you need an articulation point here, but that's not where axis 3 rotates. This is technically where axis 3 rotates, is right on down there. And so you can see how it works. And again, you can see with a linear drive, you have to still rotate in different positions. So even though it's translating out there, you need to give it freedom of movement here, here, and here. So that's what makes them a bit more complicated. And if you also look around here, you're going to see there's 1, 2, 3 motors here. These are the motors that go out to the wrist. So there is a transmission mechanism that goes through here. There's usually like some spinning axles and a bunch of gears that allow you to move all of these axes around like this. So you really have to think about the mechanics. We don't see what's going on there. It's kind of shielded, but it's kind of cool. Kuka also does something like that. So that's really neat because it's an unusual kinematic. Now, one of the other things I pointed out is that, Fennec did not bring their bot, which I think is the biggest one out there. This is like 2,300 kilograms. And this Kawasaki is 1,500 kilograms. So, and with pretty good accuracy, like sub-millimeter or repeatability. And then we have this bot here, which is 2,300 kilograms, can not just lift up a car body with like the engine and everything else in it. So they used to have these bots that before you had final assembly, were able to lift the car body up, but now they can lift like the full thing. And again, see, they even have to have two motors here, but it's a simpler kinematic than the other. Unbelievably, they only have like one motor here on the first axis. So it moves around like that, but you'll see they have two drives here and they have another two drives over here. And this works a little bit different than the other. Again, you've got this parallel kinematic where you are able to move this heavy joint back here. Or I could say, what ends up happening, is that this moves forward. And as you kind of rotate that, you have this parallelogram structure here, which is keeping the third axis fixed. You see, well, it is rotating, but it's keeping it horizontal to the ground because normally the third axis would tip also with the second axis. And then you have on the other side, these that go ahead and are able to actuate the counterbalance back there. So this linkage moves and you have this very heavy counterbalance there to try to hold the third axis back when it's trying to carry a heavy payload. And then, they have the three motors, as we can see, also up here that are able to move the wrist joints. So that's how the Fennec, I think it's the M2000 IA, but the nickname for it is Godzilla.
Maybe a quick question.
Sure.
These designs, what's the maybe pros and cons compared to what we saw like in traditional arm robots, for example?
Yeah, well, it's mainly that because they're really heavy payload, you have to go to all this other trick. And I mean, the other thing the Fennec is doing that we're not quite seeing is they also have this counterbalance here, which is like basically a big damper. I think it's like a compressed air cylinder, along with actual weight. So one of them is this one's a counterbalance the third axis. This one's a counterbalance the second axis. When the second axis goes forward, you can kind of see it moving around there. And it's trying to hold it back from going too far. And you say, oh, we've gone too far. We're not allowed to do that. Okay, so that's kind of fun to be able to see how you can break your robots, uh, even though you're not allowed to do that in reality. Now, this payload class, there's also this Titan robot. So you see Kuka was able to do it without that. This is, I think, up to also 1,000 kilogram, maybe a little bit more. And the thing about heavy payload robots is a lot of times it's not the first three axes of the problem. It's the wrist, because you're trying to carry something really heavy and the wrist is going to be up to the task as well. And so this is the Titan robot. And actually, there's a chance many people listening to the audience have ridden that robot. You might say, what? I've ridden that robot? Yes. If you go to Harry Potter World at Universal Studios and you do the tour in Hogwarts where you do the Quidditch competition, you're actually sitting on these carriages that are moving around. And there are a special version of the Titan robot that only has, I think, one of the wrist axes. The other two are kind of locked out. So it's really a 4-axis robot. And that's what's lifting you up and moving around and tipping you forward and doing all this cool stuff to make you feel like you're in a Quidditch arena. And the base of the robot is actually on a track that goes around for the whole ride. So yeah, there's a version of these for that. And then, the ABB also has its own equivalent large robot. We didn't see this at the show, but we're going to see the one that we did that was there. And finally, this is another interesting variation that I'm going to come back to that as we proceed, and some of what we saw and how this is kind of a hybrid between a palletizing robot and what we're seeing here as far as the heavy payload. So, but what I want to do is I want to continue our tour first here and get us back to the rest of the PowerPoint that we have over here. Any thoughts at this point?
Yeah, I think what you ask you this is maybe in the tour. These robots like a newest version, or
Mhm.
is this
Oh,
the
they're
new?
worldwide. They're all worldwide. Um, and even see the only version they might have is like for power, and in that case, it's more or less 50 versus 60 because in many cases they're all using like 380 or 480. So you would need to. I mean, it's factories are set up for that. These you can't bring home. The cobots you can. The cobots, a lot of them are designed for 110 in normal amperage, but these, like for industrial settings, you probably need 3-phase, everything else. so so their setup is just something I have to do in the controller. Now, as we went around, we saw another robot that was doing some palletizing, and you might remember this palletizing table that was there where the boxes were coming and getting centered and everything else. But we're just going to look at the kinematics of this. And the other robots we've been typically looking at are 6 degree of freedom, which means they can reach all positions and orientations in space. This here, whoops, let me go back to it, is only 4 degrees of freedom because it's a much simpler task of picking up boxes and you're moving them horizontally and you're dropping down horizontally. So all you have to do is turn the box in the plane, but you don't have to tip it one way or another. So it's got a different design. And if you look at it, you might be tricked into thinking it's a 5 or 6 axis robot. Now, the thing is, it's got many, let's say, joints on them, but this is considered a 4 degree of freedom robot because it only has 4 actuators in there. Axis 1, axis 2, axis 3, which is done through a tricky mechanism, and then axis 4, which is out here. And you're wondering, well, what about going on there? We're going to get to it. Look at these parallelogram structures that are going on there and what that's all about. So we'll go ahead and go back to sharing the other window here, which is going back to our robot garden. And now I'm going to go ahead and find the right view that I want to go to. And that, I think, is going to be one of these here. We already looked at that. We already looked at this one here. Oh, it's my other view somewhere in here. Yes, there it is. So there's the Nachi robot that we were just kind of looking at. And the way it's designed is you'll see when axis 2 goes forward, it's specifically designed to make sure the mounting plate right here always stays horizontal. Okay. So you see how it's kind of staying horizontal there. And then if I take this axis to go up and down, you see the same thing happens because this 4-bar mechanism is what causes that thing to rotate. There is no actuator there. It's unactuated. There is an actuator sitting right here that goes straight down that allows that to rotate. So it's really kind of a planar problem. So we can move back and forth this way with this motor. Then we have this motor here, which is actuating this thing. And the whole point of this structure here is to keep this upper structure in position that goes through this connecting linkage that we see right here. So that's the trick. And then we do have, again, some compressed air cylinders here that are used as like counterbalances because we're lifting a heavy payload. We can see that big stretch. We don't want axis 2 to have to work too hard to be able to come itself back up. And don't be fooled by the fact that this is curved. You can consider that a straight line from here to there, to there, to there. So when you draw it out, you can consider them straight lines when you do the math, but there's no reason why they can't also be curved. And so this is a very, very popular design in palletizing because it's very rigid, it's very strong, it's fewer degrees of freedom. Yeah, you could use some 6-axis robots for this, but it's really hard to get that extended reach that you want. And heck, you don't need the 4th axis and you don't need the traditional 6th axis. So what everyone calls the 6th axis is now the 4th axis, and you see that 5th axis is a freewheeling one. Basically, it follows the structure to make sure it's horizontal. And we didn't see these, but I just wanted you to see that, KUKA has a version of that as well. It's basically the same idea, the same kinematic, which means whatever the patent was on this thing ran out a long time ago. Okay. So they're all doing something similar to this, as we can see, using different means and mechanisms for being able to control the movement that's going around there. So same idea happens in many places. Yoshikawa's got one like it. All of them end up having a palletizing robot that looks something like that. So
Quick
that's,
question.
yeah.
For the curved design, we say that maybe in the modeling considers a straight line, but when designing this, what's these curvatures in which phases, like the optimization within the payload or the
Well, part of it might be that sometimes, by kind of pre-bending it, you kind of prevent it from wanting to buckle. It's already get like the tension there. But yeah, I mean, there's no reason why it can't be straight like it is here. And they probably just decide. And you see, even the Fanuc one comes around. Sometimes they might be around it because they have like right here, you're getting down very low, and you would have a collision problem if it was perfectly straight through. So that's why they curve it up like that, so it doesn't self intersect. And it could be a similar reason here. I'm not sure that it is. Yeah, it could also be that if you make that straight through and instead of having it bowed, it would come and self intersect, and they want to be able to extend their reach as much as possible. So that's the main reason. And if we look at the KUKA, you see it has a much bigger offset there than the other two. And because of that, the KUKA is probably able to get away with keeping it straight when it comes down. Yeah, and it's offset off to the side there. So you have to come down really far before that thing is going to become a problem. That's the idea behind that. Yeah. Okay. And once again, let me go ahead and get back to the PowerPoint to remind me where I'm supposed to be in the show at this point here.
I think now the second robot. Now we should move the third one.
Yeah.
Um,
So now, so we saw this one here, and then if you remember, we went over to the ABB booth, and there was this really big, was 11 degree of freedom because it's a 6-axis robot along with a 5-axis end of arm tooling here that's used for taking sheet metal out of presses and then moving it and moving them very, very quickly. So those stamping presses is that once they get up and going, they just keep going. You can't really stop them because of the inertia that's going around. So the sheet metal goes in, it comes down, presses it, and then when you're coming up, you got to jump in, pull it out as quickly as possible. Well, the next one goes in, and you're taking it from that press all the way over to the other, and they're moving it super quickly to be able to do that. And so this is a typical press tending robot that we're going to see. And so let's go ahead and take a look at the actual kinematics of that bot to get kind of an idea of what it's going to look like. And that is this ABB right over here. Okay, so there we have it. And anything that you notice different about this versus some of the others we've been looking at?
it's very horizontal. The link with the back, it's very
Yeah,
horizontal.
yeah. So it's basically using the same idea of this kinematic, and I think part of the reason they like this design is that you can put the counterbalance on here to help hold everything back. And everyone has different ways of doing counterbalancing, and so what we're going to see here is that you have this kind of, again, counterbalance here. This might be just like a big spring that's in there that's helping to hold axis 2 up. And you'll see that there's really just one on there, and on the other side, the cabling comes around. And then you have for axis 3, you have this weight here, which helped hold it back. So like that, the counterbalance isn't really needed because you don't have to worry about, but when the axis starts stretching out, you get that problem. So this is again designed, and it's designed in such a way that axis 3 rotates right about that point. There's nothing more fancy about that. That's just how that moves back and forth. And it's a fairly good reach, fairly good payload, but that's not the biggest one. So you have this one here from ABB, and you see it's kind of similar, but man, look at that counterbalance. Oh wow, that's a lot. And then look here, they got those counterbalances there on both sides, and they're much bigger than was over here on this particular version of the robot. And you can see, the wrist is really big and everything else to be able to hold it back. So again, this is an example of how you would use those to be able to hold the mechanism together and make sure everything is working right. So just wanted you to see that example and then what's out there. So we've kind of finished our trek of the heavy payload robots, and we'll get ready to move on to the next batch. Any more thoughts?
Yeah, well, maybe what downside of these robots? Like, did you notice any downsides for these designs?
Um, you When you downsize them, usually you get back. You don't have to worry about the linkage mechanisms at the back. I mean, I've seen like some smaller versions of that, but they're kind of unnecessary. And the smaller versions, you saw them because that was the only way you could actuate it because your actuators were really weak, maybe 20, 30 years ago. But now with these designs, there's no need to have the backlinks except when you get that heavy payload class. So that's when the kinematics get interesting. And then we're going to see them kind of scale down. Actually, for a second, before we go into this, let me go back as I just reminded myself, there is one more that I wanted to discuss in there before we finish it. That um, and that is this one here from Nachi. Is if you look at it, it looks really reminiscent of that palletizing bot that we've been talking about, right? We've got the same, kind of double parallelogram up there with this connecting linkage that sort of serves to hold it. I mean, they had to put a bunch of counterbalances on both sides there. I mean, it's just some, really heavy mass back there to hold it up. But you'll see that the problem with this kind of structure that we see over here is they're designed to not rotate. You can't rotate the fourth axis like all the other robots. All the other robots have a fourth axis that rotates about here. This one, you can't rotate it because you've got this structure out here that's trying to hold that wrist in a certain position. So it's almost like you go to this design, you can't have a fancy wrist. Your wrist is limited to that 1 degree of freedom you see at the end. Or is it? Okay. So what they did is they came around here and said, oh, okay, what we're going to do is that we're going to put a big wrist out here at the end. And you'll see that this is axis 3 I'm moving right now. That's the third axis that's going up there. And it's rotating this one, but it's not actuated. Okay. So it's just a follower to kind of keep this whole wrist horizontal as much as possible. But now what we can do is we can do this. So we now have an axis that rotates around in that direction there. So that gives us kind of our, I guess you could say, our fourth axis. And then we have another one that allows us to rotate around in this way. And you'll see it doesn't move very far because they really don't want it to have to. It's meant for some specific kind of applications where you don't need a whole lot of degrees of freedom. You can see the motor is right in there. They limit the degrees of freedom in that, and you can get it to move back side to side. So this is a 5-axis robot instead of a 4-axis version where they figured another way of adding something there on the wrist. What's very interesting about it is the approach that they've taken to move them out there is specific for these applications. And again, it's ginormous. It has a really heavy payload. Oh, geez, there's even a counterbalance up here. I didn't see that before. It's only when you start exercising these things you begin to notice what's going on and what's kind of needed in these different places. So yeah, cool bots that, again, if you want to see really interesting kinematics, it seems that you have to go up into the heavier payloads. Yeah. Now, so yeah,
You
I
know the
jumped
bots
the chart.
range of this
Mhm.
the price range of these bots. Do you know how the price range is?
Oh, God, those are going to be much higher. Most industrial robots, at the very low end, you can start to get like some cobots in like the 10 to 15,000, but a lot of the higher end cobots are 25 to 30. A lot of standard arms will also be kind of in that area, depending upon the options you want, kind of controller, 30, 35. These are going to go up higher. These are probably going to be more like $100,000 range, maybe a little bit more because they're more specialty. There's a lot more complex. They could be even more than that, maybe 150. Um, but then when you get all your engineering and everything done, by the time you've got it into your cell, you've probably spent $500,000 or more. That's quite common. Okay, so this was an example of a SCARA robot that we saw moving around, and I made a couple of statements about the SCARA that you can consider almost like a cylindrical robot. And now I'm going to kind of go through that just so we understand what I meant when I was talking about that. So we've got a SCARA in our little robot garden here that we're going to go ahead and take a look at. And I think somewhere, if I find my views, it will jump to the view for me. If I just go ahead and point to that part of the garden right there. All right. So there we go. An example of an Epson SCARA. And Epson, they produce a lot of SCARA robots. They come in different arm lengths and sizes and the size of your quill. I mean, it's hard to remember which model number they are because there's so many. So now the idea of a cylindrical robot is a cylindrical robot is, if you remember cylindrical coordinates, is a three-dimensional version of polar coordinates. And so polar coordinates, you have like an angle theta and a radius r that gets you out to any point in space. And if you add a z dimension that goes up and down, that makes a cylindrical coordinate. Now, usually we think of that z dimension as like coming out from the origin or something like that, but there's no reason why it has to. In this case, on these robots, this quill that goes up and down is what gives you the control of how far you go up and down in the z. And then, of course, you've got the first axis, which rotates you around. The thing is like, well, how do I control the distance from the center out to here? And in a what would be considered a pure cylindrical robot, in true to form, is that you would have a telescoping arm that goes out there. Well, if I move the second axis, it has the same effect. But the thing is, for every degree of travel that I do with the second axis, I have to do the same in the opposite direction there if I want to keep that fixed in space in these different locations. So you kind of move around there to get that. And actually, that statement I said would be absolutely true if both of these distances are the same. And in this case, I think the distances aren't the same. But I think you get the idea is that you use this to control the radius. And then once you fix your radius, just move this joint until you get that to where you want it to be. Because right now it's drawing a circle and then it goes up and down. And so that's why I'm saying is you think of it as being like a cylindrical robot where the elbow is what controls the radius. And usually that's the first thing you solve. Solve for the elbow angle. And once you know the elbow angle, you can figure out what the first axis angle has to be to get you to the XY that you want. And the Z is real easy. The Z is basically offset here. And this has one more degree of freedom that's a little bit hard to see. And that is if I zoom in really closely here, you might be able to see that this is able to rotate as well. So you can position. Usually you're talking about an application which is an XY application, and the only reason you have the Z is because you've got to jump over things. It's the idea of a pen up. Get me off the piece of paper, move over to some other location, drop down, do whatever, and occasionally you might need to rotate something. So again, it's like looking at IC chips that are being put into a PCB board. You would be picking them up and bring them over, and they might have to rotate and go in. Or as I mentioned, that if you're putting chocolates in a box and you've got a heart shape or something like that, then you have to orient it just right to make sure it drops in the right slot in the box. So that is what the SCARA robot looks like. And SCARA is spelled SCARA in all capital letters because it is an acronym, and I can never remember, but it's something to do with something like stiff, compliant, articulated robot arm or something like that. I think I get a little bit wrong, but it's something like that.
And that's a good question 'cause I remember when the SCARA robots, just not too many use cases. I feel like I
Oh, there's
didn't.
tons of them. There are so many. They're everywhere. They are, yeah. They're in pharmaceutical. They're in a lot of food. They're definitely PCB manufacturing, a lot of small parts, anything that's like a planar kind of application. And even it's like a small scale palletizing problem. So the other robots you saw for palletizing, that's a 2D problem in a sense that has like that kind of goes up. But basically everything, the problem is kind of an XY with a rotation, and then you got to stack them up in the Z. The same thing is kind of going on here with the SCARAs. And they were designed back in I think the late 70s by a professor in Japan for these really high speed applications. And so the ones that you don't see because they're like clean room and all these others, and a lot of, I mean, and there's so many different versions of these things, and every robot manufacturer has a line of them. Some of them don't necessarily build their own SCARAs. They OEM them from somewhere else. So, example, if KUKA has an application in which part of the application requires SCARA robots, and they want to integrate them into the solution, they want to make sure they have that in the library, and they do, and they white label it, or in this case, orange label it. uh, for that case, and many of them will do that. Some of them build their own. So I think Fanuc pretty much builds every of their arm types. I don't think they OEM anything because they're really pretty big. ABB may, or I'm not sure if they're. And a lot of them are OEM from from Mitsubishi or Yamaha or Epson or Denso. Those are really big. So I mean, basically, the Japanese have the corner marketed, or the mark. Yeah, they've cornered the market in scare robots.
And by the
So
way, when you were there in the show, most of these robots, they're like from China, or they find the industrial one.
there really, I mean, there were some, but most of the robots coming out of China are actually more cobots. They haven't focused on the big iron because more than half the market, and that's the growth potential, is in the cobots. And as we may have noticed at the show, is that we certainly saw a lot more cobots everywhere because that's where the market is going. And the way you want to think of it is the way the mainframe competed against the PC. So IBM and others, they in digital equipment, they didn't play with the PCs because they thought they were toys. The real computing is in the mainframes, these mini mainframes and stuff like that. But then the power of the PCs became more and more and more, and eventually it's like you almost didn't need the mainframes anymore. Everything shifted that way. So what is the mainframes didn't come down to the PC level. The PCs just started eating their lunch because it started taking over more and more applications that you typically needed these big things. Same thing's happening with the cobots, is they are muscling into a lot of these applications that were traditionally IR. Part of it is because the cobots, in my opinion, have kind of outgrown being cobots now. They have heavier payloads, they get a little bit faster, longer reach, which kind of violates the whole concept of the cobot, because it's not the arm that's the danger, it's the payload. And if you are able to carry a 30-kilogram payload, I'm not afraid of an arm being that strong. I'm afraid of the 30-kilogram payload, because the 30-kilogram payload is probably not soft and round like the cobot. It's probably got a lot of sharp edges, and it's got 30 kilograms of inertia. And when that hits you, I don't care how slow it's going to hurt. So they're moving more and more in that direction. It's like, okay. But that's what you're seeing, is the cobots are kind of displacing them, and that's why everyone's moving that direction as they get. Now, this is a cobotic arm that we saw from Igus, and this is their Rebel arm, which we'll take a quick peek at. It's a 6-axis arm, and I kind of mentioned the whole controller is like right down there in the base, which is really neat. I mean, it's very portable. You can pick it up and move it around. So this is a company in Cologne, in Germany. They make a lot of different cobotic arms, as well as arms that are kind of mobile, as well as AMRs. So this is an example of an AMR that they have. And they recently, made some headlines by announcing the fact that they're building a humanoid bot. And they're building a humanoid bot called Iggy. And here's an image from their the computer rendering that they had of it, where that what we just saw, that mobile base, is right down here. And then looks like they get a really big cowbell or something like that, or maybe they went to the Munster in Cologne and took one of the church bells down. I don't know where they got that. And then they attached on the top of it their 6-axis arm that we just take a look at, and they have a hand that's going to go on there, and then a head of some sort, which is probably going to be the display interface and also a vision system. So they showed an example of this, working as a waitress. And the other thing we saw from Iggy, or sorry, from Iggy, is the Delta robot. So this is another very interesting kind of robot that I was talking a little bit about, the fact that these arms down here are all carbon fiber and extremely light. That the really heavy actuators are right up here at the base. They never move. So no actuator is having to lift or move another actuator. So this is the idea of a parallel kinematic. Because of these really strange kind of, my mouse is rotating around there in the wrong way again. That because of the parallelograms that we see here, they're able to keep this platform down there always horizontal, and they come in at this 120 degrees, which is, makes it kind of interesting. I'm trying to do the kinematics. And these joints up here are all basically those spherical joints or Heim joints that we talked about. And it's really interesting The way they're held in is that there's like springs here and here. And so you got a carbon composite with a cup and a spherical ball right there that they just easily pop into, and they're held in place with these springs. It's really hard to believe that you get the kind of accuracy from it, but it works. And so these deltas move around. The problem with the deltas is that what if you need rotation down at the bottom? That means in some cases you'll see that they're put servos. I know Fanuc has got a version, even a 6-axis version, which is crazy that you're getting a wrist down there. But at that point, you're like your payload is shot, and you don't want to have a servo down there. So what they use is they actually have a drive shaft that goes down here. But the problem with the drive shaft, it has to change in length. So you see what's going on here, and you need a special cardan joint down here to be able to spin it. And I said that actuator was up there. So that was really hard for us to see because that's as close as I could get to the bot. So what we're going to do is we're going to go ahead and see how this works in the simulation. So we'll get an idea right there, and we can kind of look at that. And let's see if I can find where it is. If I've got my, oh, there's my view right there. Okay. So there we have the Delta bot. And the Delta bot, the inverse kinematics is really easy. The forward kinematics is like really, really tough. So I just got to select this guy here, and I want to go ahead and, yeah, let's get him into jog mode. So now what I can do is I can move that platform in any direction. And as you can see, as I'm moving the platform, we are able to see how all these joints have to move as they move around there. And you'll see how this is then telescoping. Okay, now how does the rotation work? Well, let's go in here really, really close. And you can see this is what a cardan joint is. You've probably heard me say cardan joints many, many times. And as you can see, there's an axis in this direction and an axis in that direction. And it acts as a universal joint. And you see it's able to go around in both ways. Now, this isn't very interesting because we're not off from the center. So what I need to do is like move us over here where we have a bit more of an angle. Let's really get that out at an angle. And then you'll see how that joint mechanism has to work. So as you see, as it goes around and spins, it needs to use both those degrees of freedom to be able to get that. And let me really get this off to the side. You know, let's get a really nasty angle in there. Okay, now you're going to see this a lot better. And I just got to grab the right axis there, and you'll see what it has to do. You can see how those two joints are really needed in order for it to rotate in the horizontal. So this whole structure spins around all the way up to the top to where this actuator is. And of course, you need to have the same kind of mechanism right up here, this cardan joint, that as everything is spinning, it's spinning at the same time. And let's see if I can get that to, oh, let's see, I can get axis 4. I'm just going to move axis 4 right there. So you see the green part up here, exactly how that has to work, and you get the same thing on down there. And that needs to telescope. So now I also mentioned something about what the work envelopes of these look like. And let's go ahead and show the work envelope. So that's pretty much the area that it's able to reach.
Not too
So
much. Not too much, huh?
yeah, so it's you see it has a lot of XY, but it doesn't have, let's say, a whole lot of vertical before it kind of gets out of it. So it's able to kind of get up to about there, and then it's kind of reached its limit, and then maybe down to about there, but it can come way off over to here and way off over to there. That's about what it does. And then things start to get a bit silly and out of control. But that's okay. So again, this has actually taken over a lot of the spaces that SCARAs are typically used in, because these things are so light. They are so fast, the way they're able to go around. And again, they'll be used in a lot of the food industry where you're trying to pick things off of conveyors and then box them really quick, pull them off. And they're tied to a vision system that's able to see exactly what the part is that's coming down that you need to pick off to be able to go in there. So it's a really good design. Now they all have because it's light, they all have extremely high acceleration. So the accelerations of a SCARA. Now SCARA is kind of a small robot. And so if you have a lot of speed, so if you want to have a tip speed that's, a couple meters per second, that means, and you're doing it over a short distance, you have to accelerate really fast, or you just don't have enough distance to even get up to top speed. So what's the point of bragging about a top speed if you don't have enough runway to be able to get up to that top speed? That means they have to have accelerations. The accelerations in these robots is absolutely crazy.
You
I
mean the
mean,
scale?
the
Scale.
SCARAs, and even these guys here, I mean, it's like 10G is not uncommon. there are some that will be as high as 20G. So they're just fast, and there'll be a blink of an eye. So this one that we saw at the show was not like the fastest one. They go much faster and accelerate a lot more. And when you do that, that means it has to be bolted down in something really solid. Otherwise, everything's gonna be shaking around because your acceleration is just so great. Okay, so that's now I think what ended up happening right after I was at the IGAS booth, I then wandered over to another booth, and things started to happen. Okay, so if you remember, I went over to talk about the fact that Iggy had, or not Iggy, the arm from IGAS, I get the two confused, has a controller built into it, and that a lot of other robots have a big controller. So I kind of walked over and was pointing, and this was a booth that actually wasn't showing off robots, but was showing off safety equipment. And you'll see right here is a light fence, and you see how those lights are green right there? And you see how
Yeah.
my hand is down here? I didn't think I was poking my hand in there, but evidently when I moved up, my finger just caught it and it went red. Whoops. Let me get back again here. I'll keep on loose. There we go. Get that back. And so that's Robo Fence. I apologize for whatever I did, but I proved your equipment works the way it's supposed to. I hadn't even entered. Just a little bit is enough to trigger it. And you're probably wondering, okay, how does that something like that work? Anyone seen a garage door opener, or you've gone to the supermarket checkout and you've ever wondered how the conveyor automatically stops? There's a simple little photo there that is seeing if something is breaking it. So all you need is multiple of these and you can do the same thing. And so it's really hard to visualize how that works, which is why right now I'm going to go back to the robot garden. And a lot of times this is what we will drop into our layouts is a light curtain like this. So the way the light curtain works is, as you can see, these beams are across here. And if you could visualize those beams, you would be able to figure out how to slip your arm through there without it happening. Okay. So potentially I could get my arm, but my whole body will be very difficult to do. And of course, the beams might be on or they might be off. And if you want, you could change the resolution of them to say they're only every 200 millimeters to decide where they are. And that's just going to decide what your safeties are. And that's a problem with a garage door opener. There's only one beam and everyone knows how to step over it. And the regulations are at that height for small children and dogs. So, but they're not at bumper level for some reason, which means the bumper of your car could be sticking out and the garage door will come down and smash it. So a proper garage door opener, I think, should have multiple beams going up for making sure the small pets aren't in the way and also making sure the car itself is not. So, if
So the
anyone's seen.
thing that's in the demo, this was small beam light. I think the distance was not too huge. That's why it
Yeah,
catched.
yeah. If I was lucky, I could have stuck my finger through and nothing would have happened. And so I think what happened is I was lifting my finger up just a little bit and I probably swept past it and bam, and it caught me. Okay. So that means if you want to defeat these systems, you have to be a really good burglar. It's you know, I'm just thinking of like those Tom Cruise movies and stuff like that where they have it. And usually they go out there, they throw some dust and some other things so they can actually see where the laser lights are that they can dance over them. It's the same thing. It's exactly the same thing that's going on there. So hopefully that helps everyone sort of visualize what's going on, how they're probably everyone's already figured that out, but if not, that's exactly how they work. So then other interesting things started sort of happening after this. Let's see. I think I walked over here and I get this robot like all wrong at first because I was a little bit thrown off. This is also a Kawasaki robot. It wasn't a Nachi. I was thrown off because it was in someone else's booth. And
This is Musion, no? I think that was Musion,
yeah,
maybe.
yeah, yeah, and which is an integrator. I think they were showing off the track it was on, and I was looking more at the robot itself and everything. And so I get a couple of things wrong about this, but now that we've looked at everything, we'll see a little bit more. So the one thing I want everyone to see is that in this case, you'll notice we can see an actuator down here. Is that they've actually moved some of their actuators more down on the wrist itself rather than way up on the other side. So that's a little bit of what I want to discuss right now, as well as the kinematics of this that I kind of got wrong and correct the record on that. So let's go ahead and look again. Let's go back into the robot garden and let's see from all my different views if I can find. Oh, I think it's this one right here that I want to get. All right, so we found it. So we can see it says right there. That's a Kawasaki robot. All right. So we were kind of looking at it from this side, And whoops, I moved to the wrong one right here. Let's get back. So we were looking at it from this side, and we can obviously see the first actuator here that makes joint 1 move around. And we can see over here is joint 2, which goes ahead and makes this axis move forward. And again, they have this parallelogram, but it's a little bit different. You see, they don't have that connecting rod that goes in there. This thing is stiffly on out there the whole time. It seems like it's being used kind of as a counterbalance. And this rotation right there is normally where everyone puts their axis 3, because then you just push this thing up and down and axis 3 moves, and you can get the axis 3 motor down low. But it's not there. And axis 3 is actually happening up there. So remember, when I came around there, at first I thought that motor was for axis 4, because it's a little bit thrown off why you would do that. But you'll see, and it's not Nachi that does it, it's Kawasaki, because that big beast we saw was the Kawasaki robot, remember? And it also had kind of the same idea, is that you had this platform with this offset from where traditionally everyone's axis 3 is right there. But they've decided to kind of move it up a little bit higher and put it forward for some reason. And that's where it moves. And then back here, we can see there is the servo drive that goes ahead and makes axis 4 move. But down here is where they have the motors mounted on the wrist itself to be able to get the articulation for 5 and then for 6. And I want everyone to know, this is why you put holes in your donuts here when rotating these things, so you can actually see. And that's why they all have like these 3 slots right there lined up, so you can tell where top dead center is on this. Otherwise, we would have no, if that was all covered, you would have no idea that's rotating right now, because it's hard to see something that's symmetric rotating. And this here is, yeah, and this, yeah, and this is a pin to make sure that when you mount your end of arm tooling on there, it lines up in a particular direction, that when you're in neutral position, it's where you want. Otherwise, the guys try mounting it on there and they're not sure where it goes. So this is kind of a poka-yoke kind of example that you can't screw up, because your end of arm tooling has to fit into those 3 holes and it won't be able to fit in anywhere else. So alignment is very perfect. Now, the reason why I brought this KUKA robot in over here is to kind of show, and I think we saw it in other examples, that these 3 actuators way back here behind the 3rd axis are what actually make these axes move: the 4th, the 5th, and the 6th. They're a rather interesting transmission system. And if you Google like KUKA wrist mechanism, something like that, you might see a YouTube video from I think the India Institute of Technology in Delhi, in New Delhi. And it's they open up a KUKA robot while moving around, so you can see how it works. And the transmission system is interesting, because it even has belts in it. Okay, so it has what looks like timing belts, but KUKA has a special way of doing it, that they have them pre-tensioned in both directions, that actually allows them to get rid of the backlash without having a harmonic drive for that part of the mechanism. And then they open up the 3 motors back there. Now, the result of having these 3 motors in those transmission systems is that if you move one axis, you could potentially induce the movement of another, because they're kind of relative to one another. So that means, usually if you're moving the 4th axis, you could cause the 5th axis to decide to want to move along with it, which means the 5th axis will counter rotate to keep it locked in that position. So if you say you want it at 90 degrees, it will stay at 90 degrees. However, the servo will have to rotate to keep it in that fixed position when the others are moving around. So there's some coupling that goes on between these things when you do a design that way, which is why some people like putting the actuators actually in the wrist itself, because then you don't have to worry about that coupling. It all depends upon the transmission system. And so I wanted to sort of bring that up, so everyone sort of understand that you don't get these things for free. There's always something that's going on that you have to consider in your design that could have, a deleterious effect to way things are behaving, that you need to always consider. So, yep, coupling like that. And so we've taken a look at this one, and okay, so now this is a little bit of an Easter egg. I think you might know what the Easter egg is, but as I was walking over here to MagSwitch, I ended up walking by this display of robots really quickly and didn't notice this myself until it was pointed out later on by one of my colleagues who actually did this. And that is, and we can see it a little bit better in this picture that I took with my camera, is they're showing the robots here and a simulation of the robots that was done visual components. It's right on there. I didn't even see it myself when I walked by. And then I think if you remember, so my fingers were going around breaking safety fences and stuff like that. And evidently, they're very, very powerful because if you remember, I came over here and was pointing out how they're all about this gripper technology, which is just using magnets. So if you're doing things with steel, moving a lot of steel plates around, you don't need a vacuum gripper for this. You don't need a tactical gripper, but just do it magnetically. And they're showing it could work on a variety of different arms, which is why I was pointing out. And I was pointing on there, and I was nowhere near that. Now you see the reason why that is blurry right there is that blue plate is falling off. I was like in the vicinity, but I was not touching it. And somehow by pointing down there, I guess my fingers are more powerful than I think. That thing fell. It just fell. And then there was like this big clang. And of course, what happened is everyone's heads turned and they're looking over at me, and I'm this guy in the cell phone just going out there pointing with my finger, and they all think I did it. And as I was walking around, I was getting these nasty glares and stares from everyone, like looking at me. And if you remember, I just kind of quickly walked out of there. It's like I had nothing to do with it, honest. Okay. But they're this is a cool application. They're cool people, and yeah, they're probably wondering, like, did this guy suddenly grab it or something like that? So they're probably going to the security footage now, trying to see, whether I had something to do with it. Honest, I had nothing to do with it. With my day, I was tripping. I was like making safety fencing not work. Now it caused this thing. It's like it always happens when I'm there, and we're not done yet. We're not done yet because you remember we came over and looked at this other application, which also had something to do with a gripper, showing picking up different packaging. And it was working great in all of them. And I mentioned that sometimes there will be a mispick. And as soon as that happened, remember it tried grabbing it and it didn't get it the first time. It went up there. It was an empty pick and it had to go back, which showed good error recovery and everything else. And again, point out that vacuum grippers are not always the ideal solution for everything. But again, it just seemed like, oh, okay, something about me. So some kind of distortion field. Not, I don't know if it's a reality distortion field, but definitely a distortion field. Things kept breaking when I was getting near there. So, yeah, watch out. Don't invite me to your factory, is all I'm saying. Okay. So then there was another application as we were walking around there. We were seeing that you could put a robot arm onto an AGV. And I had a video about this I put about 2 years ago, and I reposted it about 2 weeks ago. If everyone wants to go in there, and the trade-offs of when you might want to do something like that, whether you want to go ahead and have a robot arm on an AGV or not on an AGV, and we can do a quick peek of that too. And I won't go into too much detail because everyone can watch that video if you want. And what I need to do is remember to share first. Go ahead and do that. And let's see if we can go ahead and find that window. And there we go. Whoop, that's not the window I want right now. Oh, what I have to do is I have to make that one active first, and then I will get it right. So there it is. Okay. So this was called, whether is Optimus going to be a gopher? And the point of this simulation was to show different ways of sort of solving a problem of moving boxes from one place to another. You can do it with a standard conveyor. And now if you had like lots of boxes being fed here, the conveyors wins hands down because you just like lots of, but if it's a small number, you might have AGVs that are doing that, picking up from one conveyor and moving it to another. And the question is always, how does the box get onto the AGV? In some cases, they might just be able to roll on, roll off. Or you might want something like we just saw there, that you have a robot that picks it up. But then, of course, the robot has to go for the ride. It takes up maybe some space on the AGV, so you can't carry as many parts. It also adds the payload. It consumes power and everything else. So there's always the option of having a robot fixed, sitting there, picking up the box, already putting it on there, and another one waiting to receive it. So it all comes down to return on investment. Is if you have to move lots of these boxes, which means I need to have lots of AGVs doing the same thing, that means I'm going to need to have lots of robots on there. It might make more sense to go for the one in the middle where you have one dedicated here, one dedicated there. But if you are picking up from a variety of random places, which they were in that example, remember they had like a lot of bins they were picking from. Um, a single robot may not be able to service all of them. So you want it to be able to move around, pick it up. And then maybe you bring it over to random locations somewhere else. Do you want to have a bunch of idle robots just sitting around waiting for you to come over? So it's always a question, do you have the UPS, arrive without a driver? In which case you have to come down and pick up the package, or do you want the driver to bring it up? And that's what's going on. So this is not a bad solution. It just always depends upon the return on investment you calculation that you do and how many. So if I need 20 of these, I might say, oh man, that means I need 20 robots. Uh, and if I get a situation, I need 100 AMRs running around, but I've only got a few stations, I might say, just go ahead and put some robots. And the thing of showing the humanoid doing it was the idea that the humanoid is deployable, whereas these things are kind of locked down and a little bit harder to move around. So if boxes are only showing up here for like the first half hour of the day and not the rest of it, then that robot's going to sit idle. In which case, I could take the humanoid and say, "You go there now, or go over here." Using the humanoid to actually ferry it this whole distance is silly. You wouldn't want to do that. That's when it starts becoming a long haul or even a medium haul. The humanoid makes no sense. You want to use this, and I've talked about it before. We already have wheeled robots. They're called AMRs. So in the situations that we really need to have a robot which has got wheels on it, they're already there. And that was just the what I wanted to make sure we covered ahead of time before we get into the rest of it, because we haven't talked about humanoids yet.
Yeah, I
And
think there's big things happen. I think you boast about the Tesla.
yeah, yeah, there
So
was there was there was a little bit. So well, actually, before we did that, I mean, starting kind of in the humanoid is we made a quick pit stop at Archimedes Drive, and we're going to cover this in about 2 weeks. We're going to be interviewing Thibaut and his team, Casper and others, about this. So I actually had a chance to hold it in my hand. Unfortunately, they have like this demonstration unit that shows like where where the braking torque is, like that you can actually push it down at some point and it will slip for you. So that's actually an advantage they have. It may seem like a bad thing, but the thing is, at some point, all transmissions are going to fail when you overload them. And the question is, do you want them to fail gracefully and then recover, or do you require them to be serviced? So if you have gears, when they fail, it means basically a tooth breaks. And when that happens, the whole system is gummed up and it's really hard to repair. People will look at it and say they have zero teeth. I look at it the other way, is that what you do in your design, you keep on talking about adding more and more teeth. And as you add more and more teeth, the teeth get smaller and smaller and smaller. So in the limit, their size goes to zero. So you can consider an infinite number of teeth as opposed to zero teeth. And if you think it was an infinite number of teeth, then your equations work. you know, the math starts to work out when you look at it that way. And that's a reason, but they still have zero backlash as a result, because the smaller your teeth, anyways, you can reduce the backlash a little bit because there's very little room for them to go. But it also gives them the ability to slip when you give too much torque. And even though you lose calibration on the input, they are doing it on the output. So they are sensing on the output and they can always get right back in there. So it's not a disaster. They have to go over and recalibrate anything. So um,
what's special about the drive compared to
yeah,
the
yeah, it's a design worth looking at. So they're still in the very early stages. There's a lot of optimization that they're doing, but from what they explained to me, they've got a pretty good path forward that I think a lot of the robot companies will be giving them a second or third look, and some of them may actually start using it. So that's what we'll see. So that's now a competitor to harmonic drives. I don't think really anyone was using planetaries, because planetaries have like a lot of backlash. Everyone's like either harmonic drives or cycloidal drives. Those seem to be the two, as well as linear drives, which is a different one. We're just thinking of the rotaries, and this might be another one that we'll be seeing more and more of. So yeah, look forward to that episode that's coming. But then we got a chance to look at Digit, and in the video we explained a little bit. And if you look at this, you can see how Digit is rotated a little bit. You see how his torso is rotated? It doesn't have a torso axis. And again, it was able to do it because the redundancy in the hip that they have there in the legs. So that was kind of cool. We were able to see a little bit of that. Uh, Another thing is that you'll notice its leg is canted 90 degrees here, because they are now using the R axis here very effectively. Before, it used to pitter patter when I tried turning around. When you saw about a year ago, it was like watching the Titanic trying to change. Now they very quickly are able to do a 90 degree, because they just rotate that joint. Oops, let's get back to where it was. And then you'll see in the next step, they rotate back around there and put that thing down there and they're done. So the thing that was, I think, taking most of the time for them, they've now been able to improve that quite a bit. And the other thing, the huge advantage, this guy can get down low. I mean, he's really getting down low there.
this is
Uh,
where I feel like they did agility doing a great job to reach.
yeah. And that's where the name agility kind of, it's kind of agile in that sense, that they're able to get into this kind of application. That means they can reach forward a lot more, because they don't have to see this has two effects. First, you can get closer to your work. And second, this is a natural counterbalance. Okay. So as you lean forward, the weight of that is helping to allow you to lean a little bit more forward if you want. And again, they can actually lean forward because they have the redundancy here in the flexure axis that allows them to move forward. We've talked about that in hip designs as for. It's just like, hey, you actually don't need a torso to be able to lean forward. You just go ahead and do it in your hips. So yeah, that works out very well. And then I think, the last little image we had here is seeing the docking port and them coming over, being able to self dock on there. And in the movement in there, the torso is having to get in different angles and orientations, proving that they have enough flexibility to be able to do it. So props to them because uh, I think it was over 2 years ago when they first were at a big trade fair showing them working nonstop the whole time, and then they did it again and again and again and again. They're probably close to 10 trade shows now that they've been to where they're just sitting there letting everyone see it run the whole beginning of the show to the end of the show. So, yeah, and they are actually used in production. Mhm.
But by the way, which company they partner with, like logistic company? I think
It
you
was
told.
it's GXO. So GXO, I like to say is the largest logistics company you've never heard of. We've heard of UPS and Amazon and all those, but GXO is like another one of those that actually helps in the delivery of a lot of e-commerce that people are not aware of. And they go in building facilities for a lot of other companies that have online. I think they build stuff for maybe for like Target and Walmart and others that have these different distribution centers.
Do you have an idea how much is the price of these spots?
Um, I think a few years ago I don't think they're selling them anymore. They're using like a RAS model, and they are doing it at a rate which is competitive if they were hiring workers. So I think it might be somewhere between 25 and $35 an hour, because you have to fold all the overhead and everything else in there. So it's competitive with that rate. And the other thing is they are not displacing workers because when they first went into GXO, it was because GXO could not find people for the Christmas rush. There were not enough people, and they were like, "We don't know how to solve this logistics problem. Can you come in and do it?" So, and agility is also very strong. If you talk to Peggy Johnson, they say the first thing they do when they go into a company is, "Are you going to use these bots to replace workers?" And they say, "No, we just can't get them." And they kind of show it, and they say, "Okay," because they do not want to be kicking people out of jobs. They want to be able. They want to start taking over work that people just can't do or are not able to do. Now, the next one we saw was the real man, which is kind of more of a humanoid torso. It's taking these cobots, which are, while they're kind of cobotic, they're a little bit industrial in performance with harmonic drives. They're very stiff, not back drivable. So again, in my book, that keeps them from being cobotic, but they're putting them on a torso that can slide up and down. And we can see they have an exoskeleton over here that you can use to teach, and some grippers. They also are working on a more traditional humanoid arm, and believe it or not, that's the picture I took. I mean, I looked at it for a second and go, "Holy cow, it looks like a professional photographer did." I guess I had my lens clean or something like that when I took it, but that's a really nice close-up that we could not see in the video of what those linkages look like. Like I said, there are no tendons in there. You can get an idea of exactly how that works, how they pull on that. Um, yeah, it's probably one of the best pictures I think I've ever taken.
I saw this is very professional. I saw professional.
Yeah, yeah, it was very professional. I thought I like, "Oh, did I download this from some website?" No, it's actually my camera did that, believe it or not. So we can see, I mean, the mechanisms in here are again like these 4-bar mechanisms we keep talking about. You just kind of pull on one and everything articulates around. And it was very easy. I was able to go up, as we saw in the video. I could touch the fingertips and actually get everything to move. And they let me do it. It's like, can I touch it? Can I say, yeah, sure, sure, go ahead, no problem. So yeah, so Real Man, you'll probably see a little bit more of them around there because a lot of other companies are using them in different applications. So they're also on a mobile base. So even though it goes up and down, they're able to move. It's a good kind of solution for humanoid type application. We talked to Robert Scoble about this. He said that there are so many that you only need really from the torso up on these assembly tasks. Why need the mobility? And all you need to do is make them deployable, which means they should be on wheels. It doesn't mean they have to be mobile in the sense that they can drive themselves around. It just means they have to be on a platform that when I need it over there an hour from now, I can just push it on over there, put it down, clamp it down so it's in the right position, and it goes and does whatever it's supposed to and move it in. So you want to make sure you don't bolt these things down. You want to make sure that they can be redeployable in a GIF. And then the reason why you want to them make them mobile is that maybe they're moving around so much, you want them to make the decision on where they're supposed to go now, rather than someone else having to come around and move them to the right position. But yeah, you'll see more and more of applications like that coming up. And then I finally found Unitree. So I said that that they didn't supposedly have their booth, but it was just walking around. It turns out it was misnumbered in the catalog. So they claimed they were in booth 25, which was like these obscure booths, and it was like I think a number 38 or something like that. So it was like the completely wrong number. And I only found it because I went to visit an old colleague of mine that had something in like the farthest corner of the hall, and when I was like, "Oh, holy cow!" There, and he was just sitting there. They left him there overnight. I'm surprised they didn't take him back to the hotel, and he was just sitting there chilling out before it opened up. So I went and I tried, and I just everyone had probably noticed I am the world's worst cameraman. That's why I couldn't believe that hand picture was taken by me. It's like, really? I took that? So I am always forgetting to clean the lens and stuff like that. And when it comes to selfies, I can't get the framing right. But he is really little. He's much smaller than I really thought. When you see him in person, you thought, wow, he's really, really tiny. Um, and you might get a little bit of an idea from what we see over here. So here was a little bit of interaction with the crowd. They would allow it to move around. I think I got a high five in there somewhere. Now, we're going to see in a second, there is someone with a controller in the back that's controlling it very much like a drone, where they have a lot of presettings of like, go ahead and like, wave and go ahead and get ready for a high five. And another one where we do something like this to do an arm wrestling, or like you saw, just like that. Yep, there he is. He'll just push a button and it just kind of runs the macro, and then he can drive it forward and around so you get an idea what it's like. So yeah, so that's the Unitree G1 as far as seeing humanoids at the show. And finally, well, then my day ended here. So this was like one of the last. I'll have to look to see. I think I remember to take a picture of our booth, or at least someone there did. And yeah, that's where we were just towards the end of the show. And yeah, and so
And the visual
that's
components, what was there? Like in US software version, what exactly was
yeah, yeah. Basically, we were showing it. What was interesting is that so many of our customers were like right by us. It's like I said, someone came up to me afterwards during the show, and he liked the Singularity episode. He said he learned a lot about it. He says, "Oh, by the way, we use your software," and he was like, "Just two booths down." And that he was taking some ideas and thinking, maybe we could put that in their controller to make it a little bit easier for people to also visualize what's going on with the Singularity. So, and then, a lot of others were there, Kuka, which is actually owns Visual Components, their parent company. Of course, they were there. And a lot of the other companies that are using us, as we saw, Magnaswitch over there, they're working with us as well. Mhm,
one, for example, I never heard of a visual component when I was in college, like only SolidWorks, for example, FreeCAD. I'm not
mhm.
sure why. Is there a reason for that? It's really impressive.
We're
What
we're
I
yeah, we're in a lot of universities now, to the point that we actually had someone coming up saying that, yeah, we're using some of your competitor software, but every time we do a job search for new people to come in, they all have experience, on visual components coming out of universities now. So it says, oh, so we were thinking maybe we had to take a look. And
nice.
so yeah, you are seeing more of that, and like I say, a lot of our customers are,
My
yeah.
opinion, much better than SolidWorks or FreeCAD. I feel like there's a lot of things you can
Yes,
play with.
see, the thing is, SolidWorks is good for what it does, and that is designing um, parts. And we don't design parts. We're not a CAD system, and we work with a lot of SolidWorks users because we need to import it. And so SolidWorks can do so much. Some people are trying to cram an application. They're trying to cram a robotic application to SolidWorks. It's not meant for it. They could do some linkage analysis and a few other things, but at some point, you get to the level you can't do it anymore, and then the data comes in, and so we've got a very strong translator from Hoops that's able to bring in data directly from SolidWorks, directly from PTC, directly from Dassault, directly from Siemens. So all that we're able to bring in, and then people can manipulate that stuff and create their end effectors, whatever they want. So we're not trying to displace them because there's enough CAD systems out there. It's like, don't reinvent the wheel. Don't put all this mental energy and come in for the CAD system you don't need, because you don't want to compete in it. What is it that you can add above that, which is a good offering? We need geometry. There's no doubt about it. Without it, we're useless, but other people provide it for us.